Good day, everyone. In this presentation, I'm going to discuss the chemistry in computer cooling systems, understanding the role of chemistry in keeping our computers cooled. So let's start. First, what is cooling system and what is its definition and importance? So, computer cooling systems are passive or active systems that are designed to regulate and dissipate the heat generated by a computer so as to maintain optimal performance and protect the computer from damage that will occur from overheating. The primary purpose of computer cooling systems is to prevent overheating, which can lead to performance degradation, component damage, or system instability. Cooling systems in computers are essential for preventing overheating, maintaining performance, and prolonging hardware lifespan. They ensure stable operation by preventing temperature-induced fluctuations and protecting data integrity on storage devices. Effective cooling solutions prevent components like CPUs and GPUs from throttling their performance due to excessive heat, enabling them to run at their full potential by dissipating heat efficiently. Cooling systems reduce the risk of system instability, crashes, and permanent damage to hardware components. Ultimately, investing in reliable cooling systems is crucial for ensuring the reliable operation, performance, and longevity of the computer hardware. Basically, computer cooling systems serves as ventilation for your computer in order for it to not overheat and risk damaging the parts inside. So let's proceed. We're going to be talking about thermal conductivity. So thermal conductivity is defined as the ability of a material to conduct heat from its one side to the other. It is represented with thermal conductivity coefficient lambda. Smaller thermal conductivity indicates that the material has stronger heat insulation and preservation. It quantifies how effectively a material can transfer heat from one point to another. In cooling systems, thermal conductivity is crucial because it determines how efficiently heat can be transferred away from heat generating components such as our CPUs and GPUs and dissipate it to the surrounding environment. Materials with higher thermal conductivity can transfer heat more effectively, allowing for more efficient cooling and better temperature regulation within the system. Components such as heat sinks and thermal interface materials, or what we call TIMs, often utilize materials with high thermal conductivity to enhance heat dissipation and improve overall system performance. So, as you can see, the pictures provided are some of the examples of materials that have high thermal conductivity and can help our computer components stay cool and not overheat. An example of this are thermal paste, copper, and aluminum. Thermal paste, or what we call thermal greases, are commonly used to fill gaps between the CPU or the GPU and its heatsink. It improves the efficiency of heat transfer. These pastes often contain a mixture of ceramic and metallic particles suspended in a silicon or non-conductive grease base. Next is copper is one of the most widely used materials for heat sinks and heat pipes. In a cooling system in your computer, it has excellent thermal conductivity, making it highly effective at transferring heat away from the components. And last, aluminum. This what you see here is a heat sink. So aluminum is another popular material for heat sinks, as I mentioned, due to its relatively high thermal conductivity, and it is also lightweight. It's commonly used in combination with copper or a standalone material for heat sink construction. Next, there are a few types of cooling systems in a computer, but we're gonna discuss the two most common types of it. The first one is air cooling. This is the most common type of cooling systems in computers. Air cooling is a very simple method for dissipating heat but can be extremely efficient and easy to install. An air cooler consists of two parts, a heat sink and a fan. The fan sits either on top or to the side of the heatsink and pushes the air away from your CPU in order to cool the components down. The fans circulate air over the heat sinks, transferring heat away from the components and into the surrounding environment. So as you can see in the figure, the fans used to create airflow within the computer case. It directs cool air towards the heat sinks and the CPU and the components and expels hot air away from it. So the case fans, or this fans on the side, allows warm air to pass through from inside the case. Also note that some computer components such as the graphics card and the CPU have their own cooling system or have their own fans directly to their heatsink to provide focused coolings. Next is liquid cooling. A liquid cooling system is a technique used to keep a computer processor's temperature low using water as the cooling medium. This cooling mechanism provides efficient cooling and helps minimize the noise generated by higher processor speeds. Liquid cooling systems use a coolant. It is usually a mixture of water and additives to transfer heat away from the components. These systems consist of water block or a heat exchanger that comes up into direct contact with the heat source, a pump to circulate the coolant, tubing to transport the coolant, and a radiator with fans to dissipate the heat from the coolant. As you can see in the figure, if your CPU gets hot, instead of cooling it directly with a fan, you add a water block along a liquid fan and a radiator. So cold water passes through the tubes into the water block, and the water block absorbs the heat from the CPU. Because water has a higher heat capacity than air, so water can absorb a lot more heat before it increases in temperature. The heat is now then carried to the radiator, which is extremely efficient in dissipating heat. The fan is there to help cool down the water. This is why liquid cooled PCs tend to be quieter. And now that the water has cooled down again, it is sent back to the water block, and the whole process repeats over and over again. In reality, all of the pipes are completely filled with water, and it moves and mixes so fast that the whole system or the whole loop reaches a consistent temperature. Now, let's talk about thermal interface materials or TIMs and phase change materials or PCMs. So, thermal interface materials are substances used to enhance the thermal conductivity between two surfaces by filling in microscopic imperfections and air gaps, thereby improving heat transfer efficiency. The role of TIMs is crucial in computer cooling system because they facilitate the transfer of heat from the component to the heatsink. Without an effective TIM, air gaps or uneven surfaces between the components and the heatsink can hinder heat transfer, leading to a higher operating temperatures and a potential risk of overheating. TIMs come in various forms including thermal paste, thermal pads, and thermal tapes. They are selected based on factors such as their thermal conductivity, ease of application, and compatibility with the specific components and operating conditions. By optimizing heat transfer between components and heat sinks, TIMs help improve overall system performance, stability, and reliability. On the other hand, phase change materials or PCM are substances that absorb or release thermal energy during the phase transitions without a significant change in temperature. When a PCM absorbs heat, it undergoes a phase change from solid to liquid or from liquid to gas depending on its specific properties. During the process of absorbing thermal energy, the PCM transitions from a solid state to a liquid state. This transition requires the PCM to absorb heat energy from its surroundings, causing the temperature of the PCM to remain constant until the phase change is complete. The absorbed heat energy is stored within the PCM in the form of latent heat. Conversely, during the process of releasing thermal energy, the PCM transitions from a liquid state to a solid state. This transition involves the release of stored latent heat energy as the PCM solidifies. They can effectively store heat energy, and when excess heat is available, and release it when needed. So, in essence, TIMs or thermal interface materials improve thermal conductivity between two surfaces. It is usually made of compounds like thermal paste, grease, or pads, or tapes. And its advantages, they're extremely inexpensive and widely available, easy to apply and remove, and can be tailored to specific thermal conductivity requirements. While its disadvantages is typically less efficient at transferring heat compared to the PCMs and may require reapplication over time due to it drying out or due to degradation. While on the other hand, phase change materials absorbs and release thermal energy by changing phase from solid to liquid or liquid to gas and vice versa. It is often used in passive cooling systems and thermal energy storage applications. It can absorb heat while transitioning from solid to liquid phase and release heat when transitioning back to solid phase. Phase change materials provide thermal buffering and temperature regulation. So it offers a more stable temperature controls in various scenarios. Next. Next is corrosion inhibition. Corrosion inhibition refers to the process of preventing or minimizing corrosion of metal components within the computer cooling systems. This involves the use of additives or treatments in cooling fluids such as a coolant or thermal interface materials to inhibit the chemical reaction that leads to corrosion. The goal is to protect components such as heat sinks, radiators, and piping from degradation and corrosion. Corrosion inhibition in computer cooling systems help maintain the integrity, efficiency, and reliability of the system by preserving the functionality of metal components and preventing premature failure due to corrosion. Corrosion-resistant materials such as copper, aluminum, and stainless steel and certain plastics are utilized to prevent corrosion and ensure components' longevity. These materials form protective oxide layers resistant to corrosion. Corrosion inhibitors added to cooling fluids further protect the metal surfaces by forming protective layers and inhibiting corrosion-inducing chemical reactions. Proper fluid selection and regular maintenance of dissimilar metals are essentially preventive measures to minimize the risk of corrosion. Next is electrolysis prevention. But first, what does electrolysis mean? So, electrolysis is a process by which electric current is passed through a substance to effect the chemical change. The chemical change is one in which the substance loses or gains an electron through redox reaction. During electrolysis, the electrolyte is decomposed into its constituent elements or ions, which migrate towards the electrodes, where they undergo further chemical reactions in cooling systems. Electrolysis can occur when a cooling fluid, such as the coolant or water, acts as an electrolyte and an electric current passes through it. This can happen unintentionally due to stray electric currents or improperly grounded components in the cooling system. Possible impacts of electrolysis in cooling systems include corrosion, coolant degradation, and in extreme cases, it could be an electrical hazard. An example of electrolysis prevention is by using non-conductive coolants or materials in liquid cooling systems. So these coolants, such as fluids that are specifically formulated or distilled water, prevent the flow of electric current through the cooling loop, reducing the risk of electrolysis. Moreover, materials like corrosion inhibitors can be added to the coolant to further protect against corrosion and electrolysis in computer cooling systems. Regular maintenance is also a good thing. It helps ensure the effective electrolysis prevention in your cooling systems. So last are the innovation or the upcoming trends in cooling systems. I picked these three because I think they are most probable to be implemented soon. So first one is the nanofluids in cooling system. So nanofluids are engineered fluids containing nanoparticles dispersed within a base fluid. Nanofluids are gaining attention for their potential to improve heat transfer efficiency compared to traditional cooling fluids. If this got implemented, nanofluids can be an alternative in liquid cooling systems, and it can be more efficient than the regular water-based fluid. Number two, the thermoelectric coolers. Thermoelectric coolers has advantage in cooling systems, including precise temperature controls, compact form factors, and suitability where traditional cooling methods may be insufficient. They could be used as active cooling solutions to remove heat from computer components. So you can set a certain temperature for your electronic device, or let's say for example your computer, and then the constant temperature of your computer will stay at that temperature. These coolers are a quality of life change to us computer users. And lastly, liquid metal cooling. So liquid metal cooling utilizes liquid metal thermal compounds, typically consisting of gallium-based alloy, to improve heat transfer efficiency between components and heat sink. So liquid cooling can be also beneficial to us instead of thermal paste that we reapply after a year or so. Liquid metal cooling could stay forever in your CPU or GPUs because gallium-based alloy is more thermal conductive than your regular thermal paste. And that's it. Thank you for watching and listening to this presentation, and I hope you learn something new.